In this presentation, I will talk about global epistemic uncertainty quantification and its application to four-Reynolds stress models of a stratified shear layer. This is a collaborative work between myself and Robert Quinn at Penn State. The overarching objective of our efforts is to predict the wake of an underwater vehicle. RANS is still the go-to tool for problems at large Reynolds numbers and large root numbers. However, eddy viscosity type RANS models cannot handle stratification. That leads us to four Reynolds stress models. FRSMs were considered to be too costly in the 90s, but now are very much accessible. Rob's efforts focus on answering the following question: how does available FRSMs do? My work, on the other hand, answers this question: how to make use of the available high-fidelity data at low Reynolds numbers to inform an FRSM so that it gives more accurate predictions at high Reynolds numbers. The two of us work very closely in terms of validation and verification, method development, and data generation. While I'm not going to show his work here, we also work very closely with Tom at ARL. The problem I'm going to talk about today concerns with two spaces: the model space and the flow space. A point in the model space is a RANS model, and all the points becomes all possible turbulent models one can ever come up with. A point in the flow space represents a flow in the physical world, and all those flows become all flows in the world. We will have calibration data at a few limited conditions, let's say within this circle. We will have our original model. We can calibrate our original model against the calibration data by some model perturbation. This calibrated model will have an applicable range, and this applicable range potentially contains the range of calibration data. We want to know the applicable range of a calibrated model without a posteriori tests. Moreover, we want to calibrate the model such that the applicable range of the calibrated model contains not only the calibration data, but also the flows of interests. The question boils down to which terms we must calibrate for FRSMs to work at both the calibration condition and conditions of interest. The work I'm going to talk about is detailed in this paper. The underlying personnel are directly involved in the program. Let me just say a few words about the background and motivation. To begin with, it is not possible to develop a RANS model that works for all flow, and a common practice is to calibrate a RANS model before its application to flows of interest. For example, we calibrate the SA model such that it gives the logarithmic law of the wall before it is used for other wall-bounded flows. In terms of calibration, high fidelity and reliable data are available at only a few limited conditions. And we need to calibrate our RANS model to the available data in such a way that the calibrated data would also work at conditions of interest. This poses two challenges. First, how do we know the calibrated model's applicable range a priori? And second, how do we know which terms we want to calibrate? This becomes very non-trivial when FRSM is under consideration because there are many, many terms we can calibrate. This will become clear in a few slides. Those considerations lead us to uncertainty quantification, and more specifically, epistemic uncertainty quantification. The literature has quite some discussion on epistemic uncertainty quantification. However, the existing methods on epistemic uncertainty quantification are local in nature. Namely, they provide uncertainty estimates or sensitivity estimates, which probably is more to the reality for this talk, of a flow quantity to a model's perturbation to one given flow condition. However, what we want is a global epistemic uncertainty quantification. We want uncertainty quantification within an entire flow space. So let us take a look at a flow space. Flow space can typically be decomposed into different flow controlling parameter spaces. So let's take a look at flow controlling parameters. Consider, for example, stratified shear layer. The first flow controlling parameter could be the Reynolds number. The second flow controlling parameter could be the Richardson number. And those two flow controlling parameters give rise to a flow space. A point in the flow space represents a flow. And we can apply a local epistemic UQ method, which will give us uncertainty estimates at this specific flow condition, at this one condition. And we are going to denote that uncertainty or that sensitivity as EI. So let's remember this notation here. We can screen this flow parameter space by randomly sampling this in this space, as you can see here. This point represents a screening of the flow controlling parameter space. Now, if we apply a local epistemic UQ method at every point, then we'll have uncertainty estimates at all conditions. And those estimates together give a global uncertainty estimate. And this is a lot of information. To compile those information, we will take a look at those two statistics. The mean of those sensitivities, EI here, and the standard deviation of those sensitivity estimates. In all, a global UQ method consists of a local UQ method and a screening of the flow controlling parameter space. Now, if we take a look at those two parameters, I'm going to name them effectiveness and inconsistency. So the higher the sensitivity is, the higher the effectiveness is. The higher inconsistency is, the higher the standard deviation is. And this gives us 4 quadrants. We will evaluate a possible model calibration or model perturbation in terms of its effectiveness and inconsistency. A model perturbation will have a notable effect if it is in high effectiveness quadrants. There are 2 high effectiveness quadrants. And a model perturbation will generalize to conditions other than the calibration condition if it is in the low inconsistency quadrants. Again, there are 2 low inconsistency quadrants. Now let's go to the specifics. The model we're going to look at is the full Reynolds stress model. So this is the Reynolds average and Stokes equation. For FRSM, we will write transport equations for the second order moments, including the Reynolds stress, the theta, which is temperature density, the temperature velocity correlation, and the temperature variance. Many of those terms in this transport equation must be closed, and this the closure model we use. And this closure model is actually fairly popular. All right. As you can see, those many terms will give rise to a high dimensional model space. So this is our model space. Let us consider a point in the model space, and that is our original model. We can perturb a term in our original model, and that will give us another model in the vicinity of the original model. And those perturbations will be considered as a model perturbation. There are many ways we can do a model perturbation. For example, we can perturb a tensor, we can perturb a vector, or we can perturb a model coefficient. Those perturbations will add to the dimension of the model space. For example, if we perturb a tensor, we can perturb its orientation, its shape, its magnitude. That gives rise to a 6D model space. We can also perturb a vector that gives a 3D, and the model coefficient gives a 1D model space. Right. If we put all those possible model perturbations together, we have a 55 dimensional model space. And that's very high dimensional model space. So to sample this model space, we will use this so-called one at a time method. Its cost is very low. For a D-dimensional model space, it requires only D plus 1 times evaluation of the RANS model. Now, I'm not going to talk too much about the details of this one at a time method. The only thing I will mention is that this is a well-established sampling method in statistics. The reason I'm also not going to talk too much about the details about those different types of perturbations. Instead, I will give them an index. This is purposeful, and you will see my intention in a few slides. The flow I'm going to look at is a stratified shear layer. The velocity profile looks like this, and the density profile looks like this. Of course, we have lighter fluid at the top and heavier fluid at the bottom. The flow controlling parameter space is three-dimensional. We have the Reynolds number, the Richardson number, and the turbulence intensity. We're going to screen the flow controlling parameter space using the so-called lighting hypercube method. Again, I'm not going to talk too much about this method. The only thing we need to know is it is a very cost-effective method. Its cost is independent of the dimension of the flow controlling parameter space. All right. Now we can start to evaluate those two statistics, which measures the effectiveness of a certain type of model perturbation and the inconsistency of a certain type of model perturbation. So those are two statistics. So in order to get statistically converged estimates, we must sufficiently sample the model space. Those two figures shows the effectiveness and the inconsistency of perturbation 52 on the quantity of interest, which is the shear layer thickness. As we can see, we are able to get reliable estimates of a perturbation's effectiveness and inconsistency by sampling the flow controlling parameter space 100 times. A global UQ analysis requires n, which is the number of points we need to sample the flow space, and d prime, which is the number of times we need to sample the model space. That gives us 5,600 times. So a global UQ analysis requires 5,600 times evaluation of the RANS model. And therefore, this method is by no means cheap. And this is why we have to choose very cost-effective screening method for the flow controlling parameter space and for the model space. All right, now we will start to show the results. Let us first consider simple unstratified shear layer in this flow controlling parameter space, with Reynolds number ranging from 500 to 10 to the power of 8, and turbulence intensity from 1% to 20%. We will consider 9 quantities of interest. As you can see here, they include the shear layer thickness, the mean kinetic energy, the mean velocity, the mean temperature, the Reynolds stress, the velocity temperature correlation, and the temperature variance. We will show the three most effective shape perturbation, orientation perturbation, and the model coefficient perturbation. Those different perturbations will be color-coded. We will use blue color for model coefficient perturbation. We will use green color for shape perturbation. We will use orange or red color for orientation perturbation. All right. Now I'm going to switch back and forth between this slide and my next slide because I cannot list all the observation here. So, all right. So we will make a few observations. First, global epistemic uncertainty quantification identifies the most effective perturbations, and they lie to the right of this figure. This is essentially the purpose of this analysis, right? We want to identify the most effective perturbations. We will also have, and we also observe the magnitude of a perturbation does not affect the results. This essentially talks about the cross symbols and the square symbols. So we change the magnitude we perturb, we change the magnitude of how much we perturb a model. And as we can see here, this does not seem to change too much our result because the cross symbols and the square symbols are fairly close, right? And third, the analysis points to 52 and 54 as effective perturbations. So let's take a look. As you can see here, right, 52 and 54 are effective perturbations for almost all, in fact, all of our quantities of interest, right? Those two perturbations are perturbations to the production term, and this is consistent with our previous literature and it serves as a validation of our methodology. And fourth observation, for flows in this flow controlling parameter space, the effectiveness perturbations lie within the high effectiveness and low inconsistency quadrant. So this is quite obvious too. So remember, this is the low inconsistency quadrants is low in y-axis. And as you can see, most perturbations are fairly low in y-axis, means they are quite consistent throughout the entire flow controlling parameter space. Hence, calibrating the model at one condition will in general lead to improved performance at other conditions. Now, this is considering one flow quantity of interest. Fifth, we make the observation of the effective perturbations are fairly consistent between different quantities of interest. So let's take a look. For example, perturbation 54 and 52 are effective perturbations for all quantities of interest. And for example, perturbation 9 and I think 5 are the two most effective coefficient perturbations for those 9 quantities of interest. This means a perturbation that is effective for one quantity of interest is also effective for other quantities of interest, which typically means a good model is a good model for almost all quantities of interest. And this is a very desirable feature. I want to say a few more words about this observation. A few slides ago, I said I'm only going to assign an index to a certain type of model perturbation without attaching too much physical meaning to it. This is because I want to show you that even without physical understanding, we can identify something meaningful and physically make sense. Now here, we can start to use our physical understanding to see how we could get to more accurate models. Now for FRSM, the production term is closed. So perturbing the production term does not make too much sense. Nonetheless, considering that the physics is such that the production term and the dissipation term approximately balance, the results here suggest that we need a more accurate model for the dissipation term. Let's see whether that's the case. This is the dissipation term, and you probably will be surprised that FRSM, which is developed to account for flow anisotropy in the first place, itself uses an isotropic model for the dissipation term. Well, if this model is together with all the terms, I think you will not notice this, but through this analysis, this becomes quite obvious. You will hear more about this term in Rob's talk, so I will not elaborate here. All right, having validated our methodology, we now apply it to stratified shear layer. Of course, this will be a more challenging case. The results are shown in here. And as you can see, indeed, this result is, should I say, much less attractive than the one we shown before, because many of the perturbations becomes inconsistent. And if we remember, inconsistent perturbations means if we calibrate at a training condition, it is unlikely to be able to generalize to other conditions within the flow space. So this is actually very undesirable. So we want to find out why there is such a high inconsistency. Now our hypothesis is as follows. We notice that for a stratified shear layer, there is an early stage where buoyancy is not important and a later stage where buoyancy is important. This is similar to a stratified wake flow where the buoyancy is important in the near wake regime and not important in the quasi-2D regime. Now, I recall James Riley, Dr. Riley asked this question. Is the physics such that we need two models or two variants of one baseline model for the early stage and the later stage? And this methodology gives you a formal answer, I think gives a formal answer to that question. Because we have high inconsistency, we should have two models. We indeed should have two models to handle two different regimes. Now I want to put a remark here. In physics, in real world problems, it is actually usually not too difficult to know whether we need two models to accommodate different physics in the flow controlling parameter space. And the most notable example is the modeling of water turbulence. For example, the SST model practically is a blending of the K epsilon model and the K omega model. And essentially, we're using K epsilon in the near wall region and a K omega in the bulk region. Okay? Okay, to verify that this interpretation is actually correct, we're going to conduct the analysis for the early stage and the late stage separately. The results are shown here for two types of perturbations, 52 and 9, which are the two most effective perturbations. The square symbols shows results where we apply the methodology for the entire flow controlling parameter space. And blue symbol shows the results for the early stage, and the red cross symbol shows the result for the late stage. So as you can see here, by separating the late stage and early stage, we significantly lower the inconsistency, right? And that verifies our physical interpretation. Now, up to this point, I have been claiming that a model perturbation in high effectiveness and low inconsistency regime will give you something that can generalize. And any perturbation in the other quadrants won't be able to work. And I haven't really shown you any evidence, and this is where I show you the evidence. Suppose we want to do model calibration, and we have DNS data at one training condition where the growth of the shear layer thickness is shown in A in black line, like this. We want to calibrate our FRSM to our model, to our data, such that to our data at this particular condition, so that the calibrated model predicts shear layer growth more accurately at training conditions, this condition, and the other three test conditions, whose shear layer growth is shown in BCD. So BCD here as black lines. Of course, when we are calibrating, those black lines assume not known to us. The red line shows the prediction of the original uncalibrated FRSM model, as you can see here. So they are not very accurate. So now we are going to do perturbations to the original model and show results here. So first, as you can see, perturbation in the low effectiveness quadrant, which is perturbation number 1, won't have a notable effect on model's performance, even if we increase the perturbation by a factor of 10 or 20. And in fact, this is the result for perturbation number 1. And they are actually on collapse with the red line, so you really cannot see it here. But just if you perturb a low effectiveness perturbation, there's just not going to be too much effect. Now, if we perturb something in the high effectiveness and high inconsistency quadrant, which is perturbation number 2, we see that they will give us inconsistent results in flow controlling parameter space, right? As you can see here, so this is effective. So 22 is effective. So we can actually calibrate it such that we match as close as possible to data at the calibration condition. However, this line does not give us consistent results. Like at this condition, it doesn't improve much, but at this condition, it improves a lot. And at this condition, it doesn't improve much, right? So this is very inconsistent. So literally very inconsistent. And however, now if we perturb something in high effectiveness and low inconsistency regime, which is perturbation number 9, as you can see here, of course, this is high effectiveness, so we can match the training condition as 22, so we do that. And as you can see, it yields very consistent improvement at all other conditions. Maybe here it's not as great as the other two, because I mean, it's probably too much to expect that it will match perfectly, right? We can only ensure that we improve significantly, which is what we show here. So at this point, I should have shown you all the things this method can do. So I will conclude. The global UK method helps us to do those following 3 things: determine a priori a model's applicable range, and determine which terms we want to calibrate to match the data and determine if the physics in the flow controlling parameter space requires more than one model without any physical understanding of the problem. Specifically for the FRSM of stratified shear layer and stratified flow in general, we know that stratified shear layer requires different models to accommodate different physics at the early and the later stage. The production term, we found out that the production term or the dissipation term, the first term in the pressure strain correlation, essentially the rapid pressure term, and the length scale equation needs further calibration and modeling. That points us to the right direction. By calibrating a high effectiveness, low inconsistent term at one condition, the calibrated model will be able to work at other flow conditions. That's everything I want to show today. Thank you for your attention. I'll be happy to discuss with you if you could send me an email or send me a Zoom invitation.